So Charles Lyell is another interesting character in understanding Earth history. He's another Scotsman. You can see he lived from 1797 to 1875, and he traveled a lot. He traveled all over, not just Europe, but also made some trips to North America. And he ended up writing a book called The Principles of Geology. And one thing Lyell was just really good at that, for instance, Hutton wasn't so good at, was Lyell was a fantastic writer. He could write and explain scientific principles in ways that made them much easier to understand. So Principles of Geology became like the textbook for teaching geology for much of the 1800s. In fact, he had so many contributions to the science of geology that he ended up being knighted by Queen Victoria for his contributions to science. So let's take a look at Sir Charles's two principles of relative dating that concern us. Now, his principles apply to all rocks. So these are a little bit different from, say, Steno's principles, right? Steno's were only rocks that form on the surface, sedimentary and extrusive igneous. These are all of them. Now, his principle, he had the principle of cross-cutting relationships. This is that any feature that cuts across another feature must be younger than what it cuts across. Okay, that sounds kind of weird, but let's take a look at what's going on here. We have three things here. We have this white dike, we have this crack in the rock, which is called a fault, and we have the basic background kind of gray rock there. And I can say that the first thing that formed was the background gray rock. And I know that that had to be the first thing because both the white dike and the fault cut through it. And you cannot cut something that does not yet exist, right? You can't slice a loaf of bread that you haven't baked yet. And so the gray rock is first. The white dike is second, and I know that's second because the fault cuts through it and has moved that, right? This white dike used to be together, but it has been moved. It's been split by that fault. And so that's how you can use cross-cutting relationships to put things into an order of events. All right, now Steno's other important dating principle is the principle of inclusions. And that's fragments that are contained within a rock must be older than the rock they are in. Think about like a conglomerate, right? A conglomerate in sedimentary rocks is the rock made up of all kinds of pieces. Well, those pieces don't spontaneously generate in that rock. They were older pieces that got stuck together. Or, remembering igneous intrusions, we talked about xenoliths, right? Those other rocks stuck in there. This is a xenolith, but it's also an inclusion, right? It's this rock stuck within that igneous rock. And this has to be older. Okay, so that rock is older than the rock that is holding it. All right, so in your lab, and don't worry, I will have a little video that will kind of step you through your lab activity. One of the things you're going to be doing in that lab is using both Steno's and Lyell's principles to help figure out the order in which things happened on Earth. All right, another important character in the figuring out the understanding of geologic time is Will Smith. Because, I mean, we were getting jiggy with things. Well, okay, never mind. Will Smith lived from the late 1700s into the early 1800s. That's him there. He was a surveyor. And as a surveyor, surveying roads and property lines and canals and things, he traveled throughout England and Wales quite a bit. And as he was traveling throughout England and Wales, he started noticing patterns in the rocks and also in the fossils that he found. And so over the course of that time working as a surveyor, he ended up ultimately giving us two very important things in geology. He drew the first geologic map of England, and in fact, this is the first geologic map of a large area. And the other thing is he developed the principle of fossil succession. So first of all, let's take a look at his geologic map. Basically, the different colors correspond to different rock formations. And this was his map that he drew. This is a modern geologic map of Britain. And he got things pretty close. Look at these. Those are igneous intrusions. Those are spot on to the modern map. Look at this kind of shape coming in here, right? You can see that right there. And so he was was the first person to actually map out where different rock formations were located on Earth's surface. But like I said, he also worked a lot with fossils. So before we can really talk about the principle of fossil succession, we need to talk about what fossils are. And fossils are any evidence of past life. Anything that gives us some kind of clue that there was life before us. There are two major types of fossils. You can have things like body fossils. And body fossils are actual pieces of an organism. So it can be things like bones and teeth, like we see in this T-Rex skull. That's the T-Rex skull that bit me. It can be things like skin. This is the actual skin of a sauropod dinosaur. Sauropods are the big four-legged ones with long necks. But you can also have what are called trace fossils. Trace fossils are indirect evidence of past life. Like this footprint. That's a footprint of an Acrocanthosaurus, which is it looks sort of like a T-Rex with arms that work. We don't have a piece of the organism, but we do have something it left behind. It left behind that footprint. This is another trace fossil. This is something we call a coprolite. A coprolite is a piece of dung. It's a piece of poo. Definitely not a piece of the dinosaur, but it is something that it left behind. This is a dinosaur coprolite from Wyoming, and it dates to the late Jurassic. So, again, a trace fossil. Not the organism, but something it did create. All right, so those are the types of fossils. Now, what was really important about William Smith, what he recognized was fossil succession, which states that fossil organisms follow one another in time in a definite and recognizable order. And each distinct organism existed for a specific time period. And within that, we also recognize something known as index fossils. Index fossils are easy to identify. They're widespread. They live all over the place, and they live for a short geologic time. So if we find those, because they lived for a short period of time, we know that we must be in this tiny little time period. I'll give you an example of a fossil that is not a good index fossil. There's a little organism called Lingula. It looks kind of like a clam, you know, where there's two shells, except it's a brachiopod. Don't worry about it. It's like a creature with two shells, looks sort of like a clam. Lingula has existed on Earth for something like the past 550 million years, and it's still alive today. So if you find a fossil of Lingula, well, you know what it tells you? That rock with that fossil in it is from anywhere from yesterday to 550 million years ago. So that is not an index fossil. An index fossil has to exist just for a short period of time. So that helps us figure out the age of the rocks that it's in. So let's look at this. We would call this a stratigraphic section. Stratigraphy refers to studying the layers of rock. Remember, strata are layers of rock. And we see that there's these different fossils in them. And remember, the principle of fossil succession is that these organisms follow a definite sequence. So for example, this fossil is always going to be older than this fossil, which is always going to be older than that fossil, right? Definite sequence. And then here's one of those index fossils where it only existed for a short period of time. Now, what does this have to do with dating then? Well, if we find that index fossil, we know it's from a specific time period. And also we can kind of, what Smith would be able to do, he would have studied these different fossil sequences, and you could bring him a rock with a fossil in it, and he would be able to tell you, like, oh, that's definitely one of the older ones because it would have one of the older fossils in it, or it'd be like, it's one of the younger ones, so it's up here. And so it really kind of gave him this idea, this seeing how life has slowly changed and evolved over time. So that's LYELL's big contribution, and you will work a little bit with some principles of fossils in the lab for geologic time. All right, now I've talked quite a bit about how geologists read the rocks like a book, right? I even use the example, it's like reading a textbook, right? Reading a history book. Unfortunately, though, Earth is kind of like a used book. You ever go to the bookstore on campus and you buy a book, but like pages are torn out and stuff like that happens? Well, unfortunately, that's happened to Earth. We have these things called unconformities, and that's like a page being torn out of your history book. And this unconformity is a surface that represents a gap in the rock record. And so that means we don't have any records from that, right? Like if you tear that page out, you don't know what it said. So if we are trying to correctly interpret Earth's history, we need to know when our records are incomplete. So we need to be able to recognize those unconformities. Now, what causes an unconformity? Well, either erosion or non-deposition. Erosion is basically where the rocks formed, but then they got eroded or erased, right? They're gone. Or non-deposition is simply when no rocks were forming at a certain time period. And if no rocks are forming, we have no record of what was going on. And so that's our unconformities. And like I said, you've got to be able to recognize them in order to develop a proper view of Earth history. And there are three types of unconformities. The first type is called an angular unconformity. And this is where the layers above and below the unconformity are not parallel. So for example, that's what we have right here. Notice these rock layers are tilted, and then this one is horizontal. So our unconformity is right there, and these rocks are not parallel to each other. Well, what happened to form that? Basically, these rocks are sedimentary, so they were originally horizontal. Mountain building tilted them. They got eroded down, and then younger rocks were put on top. That's our angular unconformity. So the time we're missing is that time that they got tilted and eroded. Another type of unconformity is called a nonconformity. A nonconformity is a boundary between intrusive igneous or metamorphic rock and sedimentary rock. And that's what we're seeing right here. This is Lewisian gneiss. Okay, so that's gneiss, that's a metamorphic rock. This rock up here is Torridonian sandstone. Sandstone's a sedimentary rock. So right where I'm standing in that picture, that's the nonconformity. Well, what time is missing there? Well, remember, intrusive igneous rocks and metamorphic rocks form deep underground. So this rock formed deep underground. Where do sedimentary rocks form? On Earth's surface. So the time that we are missing is this rock was deep underground. The rock that used to be covering it got eroded away, and then these younger sediments got put on top of it. There's quite a bit of time missing there. How old is Lewisian gneiss? About 3.2 billion years old. And Torridonian sandstone's about 1 billion years old. And so you're missing a couple billion years in between those two rocks. All right, our last type of unconformity is a disconformity. And this is the hardest one to recognize, because a disconformity is where the layers of rock above and below the unconformity are parallel. Somewhere in here, there's actually a couple of disconformities. I don't know, it might be like here, but the rocks are parallel above and below. So it's really hard to identify. Usually what you have to do is you have to get real close and be able to see if there's like an erosional surface, or maybe the fossils inside the different rocks tell you there's a big amount of time missing. But it's definitely much harder to identify than the angular unconformity and the nonconformity. By the way, in the Grand Canyon, we do, in this photo, also have a nonconformity. Way down here. That is the Vishnu schist, and then sitting on top of it is sandstone, and so sedimentary on top of metamorphic, and right there is a nonconformity as well. In another part of the canyon, if you go a little more that way, you'd find an angular unconformity as well. Okay. Now, one thing geologists do a lot when we are studying rocks and the overall geology and history of our planet is we like to correlate rocks. And correlation is determining the equivalence of rock units. So for example, if we're trying to figure out, like, what did North America look like in the Jurassic? Well, we got to be able to find all the Jurassic rocks of North America so we can see, like, what did the Jurassic of Texas look like? What did the Jurassic of Montana look like? And so on. So we need to correlate the rocks, right? The equivalence. We need to find all the rocks from a certain time period. Well, how do we do this? Well, one way is just by looking at the rock type. So for example, again, we have two different stratigraphic sequences, stratigraphic columns here, right? We have one here and one there. And right here we're like, okay, we have gray shale, limestone, sandstone, gray shale, limestone, sandstone. So this limestone is probably the same as that one, right? We correlate it because the rock types look similar, okay? Or look, in this case, exactly the same. And that's like what we see here. This is White Mesa in New Mexico. Notice we have these kind of reddish rocks going into pink, white, and then sort of yellow. We could go like 100 kilometers away, and we've got the reddish rocks going like pink, white, and yellow. Guess what? They're exactly the same rock formations. You can correlate those. Those are from the same time period. Now, another thing you can use are fossils, especially those index fossils, right? Because those index fossils only existed during a short time period. So if you find the same index fossil here and in Montana and in France and in Morocco, you know the rocks those fossils were in come from the same time. And for example, here we're looking at fossils inside some different sequences. And if we look at area A and B, they have correlated them, right? There's our blue matching with blue, the green with the green, and so on. Well, where would area C fit into this if you look at the fossils? And where would area D fit into all of that, looking at the fossils? Ultimately, just like this, right? See, we have these blue ones going into green there, so that correlates with that. And then here we have these kind of green ones and red ones. Those would correlate. And so we can kind of see which rocks are comparative over these different distances. Now, one of the best ways you can figure out stratigraphic correlation is a unique rock layer, which we would call a marker bed. Right? It's this very, very distinctive rock that stands out from all the others, like this. Now you see that white layer right there? That is a layer of ash from Yellowstone. And that actually has been numerically dated. That is to the 640,000 years ago eruption of Yellowstone. So what that tells me then, when Yellowstone erupted, big explosion, and ash went up into the atmosphere and it settled out over a lot of the western United States. Of course, Wyoming, Montana, Colorado, New Mexico, all the Great Plains and Kansas and Oklahoma and stuff. And that ash settled down and covered the landscape 640,000 years ago. And so any place you see that ash layer like that tells you that was Earth's surface 640,000 years ago. So that's how you can correlate that. It also tells me all of this material was deposited on top since 640,000 years ago. So a marker bed, especially if you can date that marker bed numerically, can be very, very useful in correlation.